Good evening, sir. Good evening. Good evening. Hope you are all doing good. Good evening, Nagaraj sir. Good evening. Good evening, everyone. Hope you had a nice weekend. Our last meeting was on Saturday morning in Unacademy app, but our EDC discussion was, I think it was on Friday from 5:30 to 7:30. So we discussed something called Semiconductor Physics Part 2. This is going to be Part 3. Good evening, Sandri Srinivas sir. Good evening. Just waiting for uh, others to join. So once we start, we will go back to our original discussion, what we discussed in the previous sessions, and we will come back to the today's session. Probably in quite few minutes. Dear students, please comment in comment box so that uh, I can say you're online. Good evening, Pritam. Mr. Joshi, good evening. Okay. Sricharan, good evening. Sricharan, good evening. See, after sometimes if you miss my class, you can go back and see the lecture on YouTube. And if you have few doubts, you can comment. You can comment in the comment box so that I may answer your questions in the next class in general. Clear? Okay. Chalo, we'll start the class. Yeah. So as usual, we are discussing about GATE, Graduate Aptitude Test for Engineering examination. The subject is going to be electronic devices, which is there for ECE majorly for electronics and communication engineering students. And the concept of these electronic devices is required to understand other concepts for EE people also, electrical and electronic students also. This subject is important. Right? You need to understand all these concepts so that you will answer all your questions in analog electronics and other areas very easily. Without understanding all these concepts, you can't answer the questions. Okay, yeah, we'll move on. So, for those who joined for the first time, so myself, H. Shravan Kumar, having 10 plus years of teaching experience. So, and I have master's degree from JNTU Hyderabad in VLSI system design. Yeah. So I have mentored more than 10K students for GATE and ESC. And my areas of interest are EDC, the subject which we are discussing right now. The electronic devices and circuits. Electronic devices and circuits. And then I can also teach analog electronics, digital electronics, EMFT. Don't worry, these are all in pipeline. Some of the concepts from this analog electronics, will be discussed in Unacademy app. So right now I'm discussing simple diode circuits called clippers. Simple diode circuits called clippers in Unacademy app right now. You can also join me at 9 to 10 today. Every day from 5 to 7:30 we will discuss this subject called EDC. In the second half, that is after this class at from 9 to 10, as per the requirement, as per the demand by the students, we started the class in the evening 9 to 10, right? So because you will be available, so that you can ask some doubts if there are some doubts live, right? Always better to listen to me live, so that if you get some doubt, immediately you can ask. Clear? And digital also, slowly after finishing these two, we will start our discussion with deep discussion of digital electronics, and then we will also start our discussion on EMFT. This is also very important subject for GATE students. Almost I'm going to cover 42 marks in the GATE examination. Clear? Okay. Now, the first step to do, those who are not having an Unacademy learning app, for them it is very simple, sir. You can go on Play Store, you can search Unacademy learning app. So you will see this kind of thing. You can simply click on install, which you do for many applications. So this is important step, sir. This is important step. We have many wings under Unacademy. So one of them is going to be GATE and CSE. Choose this GATE and CSE as your goal. Choose this as your goal. And then, what is GATE and CSE? Graduate Application Engineering, and the CSE, ESE is Engineering Services Examination. Engineering Services Examinations. Almost we have 10,000 courses by different eminent faculty members, right? And we have specialized courses for many people like UGC NET, other NETs, and IIT JAM, NEET PG. So for even NEET PG also we have classes. But for GATE we have almost 10,000 courses nearly. So which includes all branches, right? So you can just click on plus, and then you can get something called get subscription. Once you get subscription, you'll go to the next slide, right? So we have the 12 months and 24 months subscription. We have 12 months and 24 months subscription. And if you use my code, my promo code called this promo code is so SVS10. SVS10 is my promo code. You can use this promo code and click on apply, and you'll get this. So for 24 months course, sir, this amount may vary. May vary, but you'll get 10% discount. On the whatever fees you have. So you can pay it through debit card, EMI, UPI, wallets, net banking. I think you know all these things very well. Just for the information, I'm trying to tell you these things again. So for 12 months, 22,500, and I would request those who are preparing for 2022 GATE, that is like those who are serious about this GATE for 2022, I would recommend you to go for 24 months subscription. 24 months subscription, so that you will have very good chances of listening and cracking the GATE examination, right? So one day I'll take a special session on why GATE is important, right? Yeah, I know I'm supposed to take the class. I'm just postponing that why GATE is important, or in between when time permits, I try to speak about that. Okay, yeah, let's move on. So this is the topic which we were discussing in the previous class, that is the energy band theory of crystals. So before moving forward, just let's go back and see what we have discussed in the previous class. So we have discussed about atomic energy levels. What are different atomic energy levels? So we have seen how this UV radiation, visible excitation, what is photon, what is infrared radiation, what is ionization potential. What is ionization potential, sir? What is ionization potential? What is ionization potential? The amount of energy required, by the electron, or the amount of energy required to detach the electron completely from its core, that is, so from the nucleus. Generally we know that there will be force of attraction between this electron and the nucleus. So to detach this electron from the nucleus, you need some amount of energy. That amount of energy is nothing but ionization. That amount of energy is nothing but ionization potential. In general, what happens, sir? The electron may move from one energy level to other energy level by gaining some energy, right? It may be through uh, some electric field or some photon kind of thing. So the ground state is nothing but is a normal state, right? All other are called excited states. All the electrons which are excited will not stay in the same place, and they will come back to their original states. So while they are coming back, they'll release some energy which is in the form of photons. Okay, this is what we discussed in detail, and that photon is going to be HF, and this is what we discussed. Either you can apply electric field so that electron can excite to the next level, or you can call something called photo excitation. That is when it absorbs some light, right? So this is called. And what is photoionization? The amount of energy which is required by the electron to detach completely from the nucleus, if it is supplied by a photon, then that is called photoionization. This is also very important. An electron may jump back from the electron which is jumping from level 1 to level 4 may come back to its original position from directly, that is from 4 to 1, or it can first jump from 4 to 2 and then 4 to 1, or it can also jump from 4 to 3 and 3 to 2 and 3 to 1. So multiple jumps can also happen, right? So if light photon is observed, that is what ionization, that is photoionization, which I was talking about. This is called photoionization. Mahendra, good evening. So we have discussed a simple problem, a photon of wavelength. This I don't think we need to explain you again and again, right? Very simple problem we have discussed. So, and then we have started our discussion about electronic structure of elements. To completely describe an electron, we need electron in an atom. We need 4 quantum numbers. What are they? N, L, Ml, and Ms. So N represents the shell of an electron, where L represents subshell, and Ml represents energy level in the subshell, and Ms represents the spin of the electron. So this is what Pauli's exclusion principle says, that no 2 electrons in an electron system can have same set of 4 quantum numbers. That's what I told you, right? No human beings in the world have same kind of thumb impressions, right? Similarly, no 2 electrons in an electron system will have same number of electrons. At least if N value, L value, Ml value are same, their Ms value at least should be different. So one can have Ms 1 by 2. This is Ms minus 1 by 2. This is Pauli's exclusion principle. So simply if he wants to confuse you, he may ask the same question in the examination also. So remember what is Pauli's exclusion principle. As Pauli's exclusion principle says, no 2 electrons in the electron system have a set of 4 quantum numbers, N, L, Ml, and Ms. And this is called, we started about N value, that is electronic shells. So we have each shell is called given name from the values for N. This is N is equal to 1, N is equal to 2, N is equal to 3, N is equal to 4. I think in the next, here for what are the 4 values? N is equal to 1, 2, 3, 4. I'll quickly go through all these things, sir. So L is equal to 0, 1, 2, 3, 2 minus N minus 1, and Ml is going to be 0, plus 1, minus 1, plus 2, minus 2, and plus or minus L. And Ms is going to be plus 2, minus 2. So for L is equal to 0, you have S. For N is equal to 1, you can call K, you can call K. For n is equal to 2, we can call L shell. This is M shell, right? For n is equal to 1, you have L is equal to 0 only. For n is equal to, you have 0, 1 like this. For L is equal to 0, we call S. This is orbital, S orbital, P orbital, D orbital, F orbital, G orbital, H orbital, I orbital. Different for different values of L, you will have different names also. You have different names also. This is also we have seen for n is equal to how many electrons we have? 8 electrons. Yeah, this is what I was very much interested to discuss. So for n is equal to 1, we call it as K. For n is equal to, we call L, M, N. But you can see for n is equal to 1, you have only one energy level, one subshell, only one subshell. But for n is equal to, you have two subshells, that is S subshell, P subshell, S subshell, P subshell. For n is equal to 3, you have three subshells, that is S, P, D, S, P, D. For n is equal to 4, you have S, P, D, F. For n is equal to 5, you have S, P, D, F. Then H, right? Something for n is equal to 6, n is equal to 7. For different values, you can have different things. So this is what we have seen. And for if n is equal to 5, how many electrons we have? So n is equal to 1, you can have two outermost electron, two maximum electrons in a shell. For L is equal to for L or n is equal to 2, you have 8 electrons. This is 18, 32, 50, 72, 98. Clear? Okay. This is what we think somebody asked the question. For n is equal to 5, how you are going to have this? For n is equal to 6, how you are going to have, and for n is equal to 7, right? So 50, 72, and 98 electrons will be there. And these are all called fourth group elements, monovalent. That is, if the outermost shell contains only one electron, we call monovalent. If the outermost shell contains 2 electrons, we call divalent. If the outermost shell contains 3 electrons, we call trivalent. If outermost shell has 4 electrons, we call tetravalent. If outermost shell is called having 5 electrons, pentavalent, hexavalent, whatever, right? So, but we are very much interested only about this outermost shell having 4 electrons. That we will tell you why it is important. Why it is important. Clear? So 2s to 2p2, 3s to 3p2, 4s to 4p2, 5s to 5p2, what we discussed. So there we have started energy band crystal. Yeah. This is what, sir. So each electron has some crystalline nature. So each has this kind of structure, right? So when electrons are coming together, the outer shells, the inner shells are tightly bound to the nucleus. If this is the nucleus, the inner shells are tightly bound, but the outer shell atoms can move very freely, and they can also form another new energy level called some. So for some electrons here, for some electrons here, for some electrons here, for some electrons here, like this, a new band of energies, new range of energies, energy levels are formed, right? Because of this outer electrons only. Inner electrons will not be disturbed. Inner electrons will be tightly bounded with the nucleus. Clear? But only the outer electrons can be combined or can form something new. So this is called band, and this band is nothing but it is happening because of energy level of each electron, each outer shell electron. So, and this is called energy band. This is called energy band. So this is called energy band. I think we discussed till here in the last class. Now we'll move to today's class. Yeah. So till this we have discussed, and then now we will see today's class. Till energy band we have discussed. Now let us discuss something about. Now consider a silicon atom has a reference consisting of n atoms. So if n atoms are existing, so now what we are saying, sir, n silicon atoms. So each silicon atom is having how many, sir? Each silicon atom each silicon atom has 4 valence electrons. Yes or no? Yes or no? That is 3s2 3p2 3s2 3p2 3s2 3p2 are the electrons which we have. Okay, so 3s2 3p2, totally 4 valency electrons we have. So n atoms are existing, n silicon atoms are considered. So you have n atoms. For each atom you have 4 electrons. So totally you may have 4 n electrons in the outer shell. 4 n electrons in the outer shell, right? And these are 3s2 3p2 3s2 3p2. Now assume that it is possible to vary the spacing between the atoms. So here comes, this is very important. I'll try to explain. This is very important, sir. Just concentrate here. Just concentrate here. Just concentrate here. Very important, sir. I'm just trying to draw the crystalline structure. I'm just trying to draw the crystalline structure of an atom or any material, silicon material. Crystalline structure. Crystalline structure. For each corner, we will have one atom. Let's assume for each atom, for each corner, we have one electron. Let's assume. This is what we have also discussed in the previous class, but let me tell you why I am asking here again is, this is very important to be discussed. So one electron here, one electron here, one electron here. For all the corners, let's say we have electron. This is a crystalline structure of crystalline structure. Yes or no? Yes or no? You might have studied in your +2 physics, or in engineering first year physics also you might have studied. So now what he is saying, observe very carefully, sir. Observe carefully. So whatever he is saying is, this is the distance between two silicon atoms. Right? This is one silicon atom. This is another silicon atom. So this is the distance between these two silicon atoms. What is asking us is assuming that this distance can be varied. Assume that this distance can be varied. So if we can change this distance, what do you mean by that? We can decrease or increase. When you decrease or increase, now what happens, sir? Now if you decrease, what happens, sir? Let's say this the distance between two atoms is decreased. Okay, so means you will get a smaller one. Yes or no? Yes or no, sir? You are trying to decrease the spacing between two atoms, distance between two atoms. So the size of the oh sorry. Are you listening? Good evening, Tejashwini. Am I audible to you? Are you listening? Just comment. Are you listening? Sir, you need to be very much careful. You need to have a lot of patience. Patience. The students who want to succeed in life, they need a lot of patience. The students who want to succeed in the life, they need a lot of patience. Patience is very much important, sir. Okay. Let's assume the distance is 2 meters. Sir, that is not there, but let's say 2 nanometers or 2 picometers, whatever. 2 picometers. This, assume that this is going to be 1 picometer. So the statement what he says is, assume that the distance between these two atoms can be varied. That is, the 2 picometers can be converted into 1 picometer. So now what happens, sir? Now this very important thing is, earlier the electrons which are revolving around this, the electrons which are revolving around this, let's say you have one electron here, you have another electron here. As I told you, you have the 2s2 electrons and 2p2 electrons. So in the outer orbit, how many you have? 1, 2, 3, 4, let's say. You have also 1, 2, 3, 4. So all the s orbital energies will, all s orbital electrons will come near and form a new energy level, because they are from same subshell by name S. But whereas this p subshell also electrons having, yes or no? Yes or no? Good response, Tejaswini and Mahendra. Okay. So the electrons in these corners will also get this, the p electrons will also come together and form another energy level. So let me draw something very interesting, so that I can divide completely this board into, just give me time. Let's assume this is going to be, for my convenience I am doing this. Let me divide this into 4 blocks, because I need to explain you all this very beautifully. So please listen to me carefully, sir. Listen to me carefully. Please listen to me carefully. This is a very important concept. If you understand this, you will be in joy, sir. The happiness which you will get after understanding subject will not be equivalent to anything, sir. Will not be equivalent to anything. You should experience that joy. I want you to experience the joy of learning. Joy of learning. That is the reason why we are struggling hard to explain you all this concept. We are struggling hard to explain you all this concept. Don't think that we don't have any work. So we do have lot of work. The only thing is we want to see you success. See your success. Right? This is a, assume that this is distance. If you want, I'll write interatomic distance. Interatomic distance D, and this is going to be energy E. This is energy E. Sir, what I am saying here is, you might have heard, those who are already in engineering third year or final year, they might have already heard about something called energy band. I am trying to explain you how the energy bands have come. I think you know, no faculty in your colleges might have explained. I don't think so, because they don't concentrate much on this. They will directly explain you what is energy band. But I am trying to explain you why that energy band has come. Why that energy band has come, which is very much important. Which is very much important. Now, so now as I told you initially, so for this case, all the 2s electrons will come together and form one energy level, right? All the p electrons will come together and form another energy level, energy level. So assume that you have so one energy level here, one energy level here. So the energy level is because of this energy level is because of, let's say, S, right? Assume that this energy level is because of P, right? So this is how many electrons you have, sir? How many electrons in S energy level? This is P energy level. So this is going to be P energy level. So you need patience to understand all this concept. So once the concepts are clear, you can easily crack the gate exam. You can easily crack the gate exam. Nagesh, good evening. Sir, good evening, sir. Nagesh Kumar, sir, good evening. So this is very important. This is energy level, the energy band theory of the crystals, which is very important. Now, what I told you, sir, how many electrons, how many atoms I have considered? I have considered two n atoms. Each n atom will have two s electrons. So how many electrons? This is a 2n electrons. 2n electrons we have. How many states we have? Only 2n states. Are you able to understand or not? Let me explain you again. So each electron of s orbital has 2 electrons. So how many atoms I have considered? N atoms. N atoms. So how many total energy electrons? 2n electrons. How many electrons? 2n electrons. So how many states you have? 2n states. That is each, this is 3s. So each electron, right? So each electron has, so total 2n states. Now how many p is having, sir? P is also having 2 electrons, and how many atoms? N atoms. So how many atoms? N atoms. So the p subshell is having 2n electrons total. But how many states it has, sir? This is very important to understand now. Understand here. Sir, concentrate. Please concentrate here. Very important. Very important. Don't miss it. This is very important. So here you can accommodate 2 electrons. Here you can accommodate 2 electrons. Here you can accommodate 2 electrons if it is P. But you have 2p2 only. So 2p2 means how many? Only 2 electrons. That is 1. This is 2. So still how many are vacant, sir? How many are vacant? 4 vacant. 4 vacant. Right? 4 vacant states are there. 4 vacant states are there. So here 2n electrons for 2n states for S energy level. For P energy level, you have 6n states. 6n states. And how many electrons? You have only 2n electrons. You have only 2n electrons. 2n electrons. 2n electrons. Now what is saying, sir? The distance between the interatomic distance is decreased. That means what happens if the interatomic distance is decreased? This is the earlier one. This is also earlier one. This is for S energy. This is for S. This is for P. This is for P. Now, when the interatomic distance is decreased, that is what happens, sir? This again, I'll go back to this. Oh, sorry. So what's happening, sir? The interatomic distance, that is, this distance is decreased. Whenever this is decreased, now what happens, sir? These energy levels, these energy levels are coming closer. Yes or no? Here it was 2 picometers, it is 1 picometer, right? Now what happens, sir? The energy levels here start spreading because so now earlier, let's say this distance, this distance is, let us say, 2 picometers. Now the distance is decreased to 1 picometer. 1 picometer. Now the energy level, which was very constant, when it is coming closer in a small space, the S energy and P energy should be accommodated. The S energy and P energy should be accommodated. Okay, Tejaswini. S electrons energy level and P energy levels has to be decreased. Sir, now we are coming back, not going forward. We are coming back. So the energy levels is decreased. Now what happens, sir? They start spreading. The energy level starts spreading. The energy levels start spreading like this. The energy level starts spreading. Understand? Okay. No, understands. Let's say you still further decreased. Let's say you still further decreased. So from 1 picometer to, let's say, 0.75 picometers. And just for the sake of convenience, for example, I'm taking, sir. Don't think that the value is correct. That the value is correct, right? Don't think whatever I said is correct. But for sake of convenience, earlier it was this is picture 1. This is picture 2. This is picture 3. For next also you should understand, right? Picture 3. So picture 3, 1 minute. I'll put all of them in the same place so that you'll understand. I'll put this is 1, so that this place is 2, this is 3, and this is 4. Because after some time also you should not. So what is I told, sir? This is 1. So let us consider somewhere around 0.75 nanometers, 75 picometers. Now what happened? Beauty here, look at here, sir. This is the beauty. This is the beauty you should understand. Slowly these two will come. These two will come and join. These two will come and join. So how it becomes? It becomes like this. So all the energy levels will come together. All the energy levels will come together. All energy levels will come together. All the energy levels will come together. So it is nothing but, now what happens, sir? If you see, it is just like this. One electron. Earlier you had electron 1, electron 2. This electron will come here. So this is s orbital, this is p orbital electrons. So all of them will come. So all these 4 energy levels, these 6n states and this 2n states will come together and form a new state called combined 8 energy states. 8n states will come. But how many electrons? These 2 electrons and these 2 electrons, total 4n electrons. Okay, all of them will come together, sir. All of them will come together and form a new range. That is 8n states, and how many are filled? Only 4 electrons are filled. Out of 8n states, 4 is, that is 50%. 50% energy levels are filled. 50% energy levels are filled. Let's assume you are still again trying to again trying to move towards the, or you're trying to decrease the interatomic distance. right? So this interatomic distance, you are trying to distance, let's say again this has become 0.5 picometers, 0.5 picometers for the example I am telling, sir. Okay. So now what happens, see, the beauty comes here. This is very important, sir. If you understand this concept, the next concept is easy. So far what we have discussed is there exists some energy band, right? Now we will discuss how the valency band and conduction band will form. Many of you might have already heard about valency band and conduction band. Now today we are discovering how the valency band and conduction band are formed. Now assume that your interatomic energy levels are again still closely coming together. Still, you are still trying to push it. You are still trying to push it. So now what happens? This is very much important to remember, understand. This was what we discussed. This is very important, sir. This is very important. Here comes the beauty of the formation of energy levels. Formation of energy levels. So see, this is how the see, now what I'm saying is, so let's say this is going to be 0.5 picometers. Earlier it was 0.75, it is 0.5 picometers. Now what happened, see, what happened is the energy levels are combined. All the energy levels are combined here. All the energy levels are combined here, which contains this contains here 4n free electrons. Electrons of 4n states. 4n states. Now this upper part, you can see this upper part. You can see this upper part. This is having 4n states. 4n states. Already all the free electrons are occupied here. So how many electrons we have? We are having only 0 electrons. You have 0 electrons. You have 0 electrons. Now here comes the beauty, sir. This energy region which is having filled electrons is called valency band. And this energy states, this foreign energy state which doesn't have any electron is called conduction band. Conduction band. Now here comes that most important thing. The gap between these two, the gap between these two is nothing but energy gap. Why 0 electrons? Because all the electrons are at lower level. Mahendra, all the electrons are at 0 level. Sorry, all the electrons are 4 electrons. Total how many in a silicon atom? How many electrons are there in the outer shell, sir? Outer shell, only 4 electrons, because 3s2 we have discussed in the previous. Let me show you here. 3s2 3p2. Out of 8 states, you have only 4 electrons. Only 4 electrons, and all those 4 electrons will be here. All those 4 electrons will be here. Okay. all the 4 electrons will be here. That is 4 electrons for 4 states. Here 4 states and 0 electrons. So this is called valency band and this is called conduction band. So let me explain you all 1, 2, 3, 4 again. 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 In the first state, what we are saying, sir, the interatomic distance is just 2 picometers. So now you have 2s energy levels. 2s energy, for energy levels, you have 2n electrons and 2n states. For P, now what happens, sir? For P, what happens, sir? You have 6n states. 2n, so this n indicates the number of atoms. Need not worry. 6 states you have, only 2 states are filled. Now what I am trying to do in the second diagram is I am trying to decrease from 2 picometers to 1 picometer distance. When you are trying to decrease the interatomic gap, the energy levels has to occupy in the same distance. So now what happens is they start spreading. When they start spreading, what's happening, sir? Now you can see this is spreading. Initially this is okay. For 2n states, you have 2n electrons. Here also for 6n states, you have 2n electrons only. Now I am trying to decrease more. When you try to decrease the more, these two energy levels will come together. And how many states? This 6n state, this 2n states. So totally 1, 2, 3, 4, 5, 6, 7, 8. So total 8n states are there. Out of which how many are filled, sir? Only 4n electrons are filled. What is states? States is nothing but this here. See, let's say consider S. Right? You have energy level. State is nothing but energy level. Level of energy. So here you have 2. One state is here, another state here. Similarly, in case of P, how many states you have? 6 states. So 1, 2, 3, 4, 5, 6. So here you have 2 states. Here you have 6 states. That is what that the value of ml represents. In the previous class, we have discussed that what ml represents. ml represents the energy state or energy level, right? So all these energy levels will combine. So becomes 8n states, and out of which only 4 electrons are there. 4 electrons are there. Clear? 4 electrons are there. So now what happened, sir? Now what happened? Still you are trying to decrease. When you are still trying to decrease, now what happens is these 4 electrons and these 4 electrons are filled states. Will come to one area. All non-filled states go to another area. That is, like I'm just trying to zoom. If you zoom it, what happens, sir? Zoom it. Zoom it and see. These are all filled states. These are all empty states, which doesn't have electrons. So as this empty state is called conduction band. And this filled state is called valency band. And important thing here is, this is the energy gap. These are the states in which no electron will be found. Either electron should be in this region or in this region. Right? So it is not possible. So the electron can't be in this region. Either it has to be in valency state or valency region or in conduction region. So there is a gap. And this is nothing but This is nothing but energy gap, which can also be represented by Eg. Clear? Very clear, sir. Right? So this is the very important concept. How did you get, sorry, energy gap Eg? How did you get this Eg? How did you get this valency band? How did you get this conduction band? Right? Why this is called valence bands are all the electrons, free electrons are present in one area, but their energy, another energy level is there where they can conduct. How they can conduct? If they can gain some energy and they move from this valency state to conduction state. Valency state to conduction state. Hope is it clear, Mahendra? Hope is it clear, Mahendra, for you? Is it okay? Is it clear for you? Okay, okay. We'll move forward then. There's a little bit delay in streaming and what we am getting here. Okay, so that is the reason why. So it might be a gap. So now you understand that how this conduction band and valency band has formed. Valency band has formed. Clear? So here we have foreign states and foreign electrons. Foreign states. Out of which all foreign electrons are occupied. And you have foreign states. Here you have 0 electrons. It is 0 electrons. If any electron wants to go from valency band to conduction band, it needs to gain some energy. So based on this concept, next comes, this is not decrease. This is what we discussed, not required. Based on this concept, we can divide. We can say what is an insulator, what is an conductor, what is a semiconductor. So here comes, now see what is saying, sir, it is insulator. Insulator, right? In the previous class, what we said is a electron which is in the valency band can jump to conduction band by gaining some energy. So it's remember, either electron can be here or here. It can't be here. No existence of electron in this region. Either it should be here in valency band or it should be in conduction band, sir. Remember that. Clear? So now based on this concept, now we will based on the concept of energy gap, now we will say what is an insulator. We will say what is an insulator. We'll say what is an insulator. I can call this as a valency band and conduction band. What is this, sir? What is this? The distance between The distance between conduction band and valency band is easy. The energy gap. If the energy gap is 6 electron volts or more, then it is called insulator. Because if the energy gap is more than 6 electron volts, the electrons in the valency band cannot jump from valency band to conduction band. They can't jump from valency band to conduction band. It is not possible. When the electron is only bind to its core atom's nucleus, it can't move. It can't contribute for electricity. It can't contribute for electricity because the conduction of electrons or movement of electrons is nothing but current. Current is nothing but electricity in general we call. So very poor conductors of electricity is called an insulator. So its energy gap is always, remember, the energy gap of a insulator. The energy gap of an insulator is nearly 6 electron volts. What are the examples for this? Is diamond. Diamond and insulator. Can somebody tell me another example for this insulator? Another example for insulator. Can you try? Can you try? Will you please try? Any other examples? Any other examples? Wood, rubber, correct. Wood, correct. Wood. Good. Very good. Very good. Very good, Mahendra. Plastic, correct. Rubber, plastic, correct. These are the examples for insulator. So based on the energy gap, the materials are classified into insulators, metals and conductors and semiconductors, right? Insulator, conductor and semiconductor or a metal. Now let's move on to the next. So what is a metal? An excellent conductor of electricity is called as a metal. As a metal. Now I will draw for you. So based on the concept of energy gap only, we are defining. Based on the concept of energy gap only, we are classifying the materials. Classifying the materials. Classifying the materials. Classifying the materials. We are just trying to classify the materials based on the concept of this. Based on the concept of this. Assume that this is this is very important, sir. You may think that why I spent a lot of time on the previous this is because you can see is there energy gap. So all these green lines indicates what? Conduction band. All these blue lines indicates valence band. See now these two are overlapped. Both conduction band and valency band are overlapped. it means you have lot of conductivity. You have many free electrons which will be automatically moving from very easily moving from valency band to conduction bands. So the energy gap is going to be what? The energy gap of an electron, sorry, energy gap of a metal is 0. And you don't have any holes. No holes. I'll tell you the concept of holes in 1 minute. In 1 minute. Just give me some time. Can somebody know holes? Only electrons are existing. What are the examples, sir? Examples of metal. You have a gold, you have a silver, you have a iron, whatever. All these things which are having free electrons, whose energy gap is 0. No energy gap. No energy gap at all. No energy gap at all. So they are called metals. They are called metals. Next, here comes something called semiconductor. Here called something called semiconductor. So what is semiconductor, sir? What is semiconductor? I'll show you again. So by definition, what is saying, sir? A substance whose conductivity lies between insulator and metal is known as semiconductor. 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 This is energy gap, right? This is energy gap. This is energy gap, right? Which is almost equal to the energy gap, sorry. The energy gap Eg is equal to nearly 1 electron volt. In the range of 1 electron volt. This is conduction band. This is valence band. So the energy gap of a semiconductor is in the range of 1 electron volt. It means the electrons which are present in the valency band can gain a small amount of energy and they can move from valency band to conduction band. Valency band to conduction band. Valency band to conduction band. Right? So whenever electron moves from whenever electron moves from valency band to conduction band, now the electron which is present here, so it is moved from conduction valency band to conduction band. Let's say it has come here. So now you can see a empty space is available here. The empty space is available here. The empty space which is available here is called as hole. And the electron is in the conduction band. This is valence band. Remember, sir, the absence of electron in valency band, the absence of electron in valence band is called as hole. Is called as hole. Is called as copper. Correct. Copper. Correct. Copper. Correct. Teshni. Correct. So the absence of electron in valence band is called as hole. So you can see the previous class, the energy gap, if the energy gap is in the range of 6 electron volts, it is called insulator. If the energy gap is 0, it is called metal. If the energy gap is in the range of 1 electron volt, it is called what, sir? What it is called? It is called a semiconductor whose conductivity lies between insulator and metal. Insulator and metal. So now how the electron can move from one state to other state? How the electron can move from one state to other state? Very simple, sir. The energy gap depends on temperature. So as the temperature increases, electrons gain energy and moves to where, sir? Conduction band. The electrons which are in valence band, This is a natural process. See, children, maybe all the non-metals are semiconductors. All the non-metals means what? I have told you insulators also. All non-metals can be insulators also, right? Not just all metals. So all the materials are divided into these three. Those who's having a range of 1 electron volts energy gap, they are called semiconductors. Insulators, it is not possible. Metals are already existing. In the metal, there is no hole. Only electrons are existing. When hole will come, sir? When hole will come? The concept of hole will come only when electrons in the valency shell go to the next level. There is no possibility at all. Electrons are already freely moving. Freely electrons are available. The electrons need not go from one level to other level in metal. All electrons are existing freely. All electrons are existing freely. Clear? So, semiconductors and metals are different. Semiconductors and metals are different. So, as the temperature increases, electrons gain energy and they move to conduction band. But at, so this is very important. At 0 degrees Kelvin, no conduction. So, when there is no conduction, semiconductor acts as an insulator. Acts as an insulator. So this point is a very important point. Many times in the gate examination or many times, what happens, sir? Because at 0 degrees Kelvin, no conduction. Why no conduction, sir? Valency electrons will not gain any energy at 0 degrees Kelvin. As I told you, as the temperature increases, electrons gain energy. At 0 degrees Kelvin, electrons cannot gain any energy. Electrons cannot gain any energy. So because of that, no conduction. All electrons will be in valency band only. When all electrons in the valency band, no conduction. When there is no conduction, what we can call? We can call it as an insulator. Very important to remember, sir. This is very important point to be remember. So what is the energy? But at room temperature, what happens? At room temperature, what happens, sir? The electrons can gain energy and they can become semiconductors. Few of the at room temperature. At room temperatures, electrons gain some energy. Electrons gain or electrons gain some energy. Gain energy. Energy. Gain energy and go to conduction band. Conduction band. Conduction band forms what? Forms holes. Holes in valency band. Holes in valency band. Okay, at room temperature, electrons gain energy. Conduction band. They move from conduction band and forms holes in valency band. So now what happens, sir? Slowly, electrons are there in both. Electrons are existing in conduction band. So when the electrons are in conduction band, they can conduct. But it doesn't have, and it also have holes. But in case of metals, there is no hole at all, sir. In case of semiconductor only. In case of semiconductor only. So now the conductivity is increased. Here it is an insulator. So we can call this as semiconductor. 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 We can call this as a semiconductor. Clear? This is called semiconductor. This is a very important concept, sir. Right? So now what is an intrinsic semiconductor? If as temperature increases, conductivity increases. As temperature increases, conductivity increases. And these semiconductors are called intrinsic semiconductor. Intrinsic semiconductor, or we can call it as pure semiconductors. So why it is called pure? We are not adding any external atom. All are silicon only. All are silicon only. We are not adding anything to it. If you are adding some other atoms to it, is called extrinsic semiconductor. Extrinsic semiconductor. This is very important. It's very important. Now we have some note here. How temperature, how silicon. Sir, the energy gap of silicon. Energy gap of silicon semiconductor material is 1.21 electron volts, whereas germanium has 0.785 electron volts. Energy gap Eg. Energy gap Eg of, so these are two important values to be remembered. The energy gap of a silicon is 1.21 electron volts and germanium is 0.785 electron volts. As I told you, as the energy gap depends on adds Eg as Eg, I can call Eg depends on temperature. So what's the formula? So for silicon, for silicon, the energy gap is equal to 1.21 minus 3.6 into 10 to the power of minus 4 T electron volts. For germanium, energy gap as a function of T, that is temperature, this is going to be 0.785 minus 2.3 into 10 to the power of minus 4 volts. These are the two important formulas you need to remember. We may get some problems on this. Simple problems you may ask. So where T stands for absolute temperature, this is important formula, this is important formula, so this is important formula. We can do some problems also. Right? So this is very important. So time and again I am mentioning, these two are important. As the temperature increases, the energy gap decreases. Yes or no? As temperature increases, conductivity increases, means energy gap decreases, because this is minus. So as temperature increases, Eg, energy gap decreases. This is a very important point to be remembered. Clear? So as temperature increases, energy gap decreases. At room temperature, at 300 degrees Kelvin, energy gap of, this is also important, sir. At what is 300 degrees Kelvin? This means room temperature. At room temperature, 300 degrees Kelvin, that room temperature, the energy gap of silicon atom, how much? Can somebody tell me? It is going to be 1.1 electron volts, and here it is going to be 0.72 electron volts. Simple, sir. Substitute 300 here in the previous. Here just you substitute 300. If you substitute 300, you will get these values. So this also to be remembered. Very important to remember. This also to be very much you need to remember. Is carbon a semiconductor? Question is, this very important question. Is carbon a semiconductor? Is carbon a semiconductor? Is carbon a semiconductor? Answer is no. But it has 4 electrons in valency shell. But the issue is, this is important. All electrons are tightly tightly bonded to the nucleus. Because of that reason, carbon cannot be called as a semiconductor. Very tightly bonded to the nucleus. That is the reason why cannot be called as a. Correct. It's not semiconductor. Correct, Mahendra. It's at large energy gap. Correct. Why it is energy gap is very high, sir? Because correct. Whatever Mahendra told is correct. EG is very high. Energy gap is very high. This point also very much important. This point is also very much important. Energy gap is very high. Energy gap is very high. That is the reason why. That is the reason why carbon is not a semiconductor. All electrons are tightly bonded to the nucleus. They are very close to the nucleus, and the energy, whatever energy you are giving, is not sufficient for the electron to go away from the nucleus in the atom. That is the reason why carbon is not a semiconductor. Okay. For information sake, if somebody asks, you can say. Right now, we'll move forward. Orbital model of silicon atom. This is very important. This is very important. I try to draw different shapes so that so you will have some. So, how many electrons total? How many electrons are there in silicon, sir? Can somebody tell me how many electrons total you have in silicon? That is, what is the electronic configuration of silicon? Atomic number. Atomic number. Can somebody say? Can somebody say, sir? No? Not interested? Array, try karo, bhai. Try karo, please. You know the answer. You know the answer. You know the answer. You know it. Only thing is, you should recollect. You should recollect. You just recollect. Just recollect. You just recollect. One is two, 1 is 2. 1 is 2, 2 is 2, 2p6, 3 is 2, 3p2. Assume that this is the orbital model of silicon. How many electrons are there, sir? How many electrons? Total you have 14. So what is electronic configuration? 1s2, 2s2, 2p6, 3s2, 3p6. So how many electrons here? You have 2 electrons, 1 electron here, 1 electron here. Revolving. Next 2s2, 2p6. So here 2s2, 2s2. Next 2p6. P6. 1, 2, 3, 4, 5, 6 electrons. 6 electrons. Okay, next 3s2. You may have a 3s2. Here 1 electron. Here 1 electron. Next 3p2. This is 3p2. This is 3p2. You see what I am trying to do is here this is 1s2. This is 2s2, 2p6, 3s2, 3p2. So this color represents 1s2. This blue represents 2, 2s2, 2p6. N is equal to 2. N is equal to 2. Energy level, N is equal to 2. This is 3, third energy level. Third energy level. Right? So what is this called? This 14 is nothing but it is nucleus. 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 And these electrons are called core electrons. Core electrons. Core electrons. Core electrons. Right? And these two are called this one and then this one. This red one is nothing but valence orbits. Valence orbits. And this blue is called inner orbits. Then what is this? This is first excitation. First excitation orbit. Means what? The electron will jump from whichever electron is jumping, that has to reach this energy level. Right? This is imaginary, sir. This is imaginary. The electron may jump from here and here. This is imaginary. This is an imaginary one. Silicon 14, correct. Correctation, correct. 4 valence electrons you have. 3p2, correct. 3s2, 3p2. So this is what the orbital model of silicon. Right? And in the crystal model means, as I told you earlier, crystal model means you have at the corners of the cube you will have. At the corners of the cube you will have. This is what the orbital model of a silicon. This are I took colors differently because you will understand differently. Right? So co-electrons and nucleus, and this is excitation. Once the electron excites, it will go to the next level here. It will go to the next level here. Is it clear? Hope it is clear for all of you. Okay. So this is the nucleus where all the protons and neutrons are existing. Out of which we have next immediate it will be is the core electron, and then we call it as inner orbit, that is 2s2 2p6 inner orbit, and the 3s2 3p2 is called valency orbits, and this one is called first excitation. This one is called first excitation orbit. So whichever electron gets some energy will move from this to this. So this is the orbital model of a silicon. This is very important, sir. This you need to remember. Next, what is type of semiconductor? Types of semiconductors. So I'll try to explain you in detail now. A semiconductor can be classified into two types. One is called intrinsic. The other one is called extrinsic. They can be classified into two types. One is called intrinsic semiconductor, the other is called extrinsic. So what is extrinsic? This is pure, or it is called pure, or extrinsic or impure semiconductor. What do you mean by impure? Adding other group elements. How a intrinsic semiconductor will become extrinsic? Why not germanium? Why not germanium? What is Mahindra? What is germanium? Why not germanium? What do you say? What is your question? Can you please ask the question clearly? Now, meanwhile, I'll finish up this classification. This is again called N type. This is P type. Yeah. What do you mean, sir? What do you mean? So, do you think? So, why only this silicon atom? Germanium is bigger one, sir. You can have 4s2, 4p2. You need many number of circles. That is the reason why I'm not drawing. You can draw, sir. You can draw on your own. No, we use some places in germanium also. So, you might be thinking that, Acha, we have a very good question. So, silicon is abundantly available in nature. Silicon is abundantly available in nature. Silicon is abundantly available in the nature. That is the reason why we use the silicon for many places. Right? Abundantly available. First reason is silicon is abundantly available when compared with germanium. That is the reason why we are using silicon, not germanium. We are using germanium also in many places, but the availability of silicon, because what is silicon, sir? From where we get? We get from SiO2. What is SiO2? Is sand. Everywhere the sand is existing or not? Everywhere sand is existing or not? So silicon SiO2 is available. So Si is available a lot. So from oxidation process, this O2 is removed. Deoxidation. When you remove, you will get a silicon vapor. So from silicon vapor, we use other semiconductor materials. That's it. Ante. That's it. So these are all two types. So one is N type, the other one is P type. One is N type, the other one is P type. So impure. Okay. Semiconductors are of two types. Intrinsic semiconductor. Yeah, pure form of silica is called silicon. Okay. Yeah. That's correct. So N type and P type. This is, so semiconductor will be classified into intrinsic semiconductor, extrinsic semiconductor. Extrinsic semiconductor may contain two, N type and P type. Clear? Is it clear? Okay, we'll go to the next slide. So the transport phenomenon in semiconductor. What is mean by transport? What do you mean by transport? Is how conductivity happens. How conductivity happens. How conductivity happens. This is very important, sir. How conductivity happens. Okay. The current in a metal is due to flow of negative charges or electrons. Yes or no? Earlier only we have discussed. Because there is no energy gap. The energy gap is zero. No possibility, no hole. No possibility of hole. In a metal, energy gap is 0 and no holes existing. So when there is no hole existing, how the current will exist, sir? So in a metal, current is only due to the flow of negative charges. Due to the flow of negative charges, no possibility of hole. When there is no hole, no hole will not move. So that is what. So in a semiconductors, the current results from the movement of both negative charges and positive charge. Both positive charge and negative charge. So we will discuss in detail about this, right? How you might have heard how electrons will move, but what is the concept of positive charge movement of holes? When electron is moving, how the holes are moving? What is the relationship? So, but predominantly due to either electrons or holes. Though electrons and holes are existing, either current, either hole current or electron current is higher. The second one is very low. In a semiconductor, as there exists a current due to negative charges and due to positive charges, but it is predominantly, it may be either both are existing, but here no IP is 0 here. Only electron current is existing. But in semiconductor, both are existing, but either one of them is high. Either hole current is high or electron current is high. Clear? The transport charges in a crystal under the influence of electric field and also as a result of non-uniform concentration. This is very important. In a crystal, electric field, if you apply external electric field, electrons and holes will move. Or there is another current which is because of the non-uniform concentration of gradient, concentration gradient. Okay. So either, let's say some semiconductor you have. So the electrons or holes may move. So electron current or some move because of some external electric field, some voltage you apply. Or also you can have let's say this is something. Let's say you have more electrons. There more electrons are existing in this region. So the more electrons may move from here to higher potential, lower potential without any. So it is very simple, sir. Very simple. Let's consider two tanks. Let's consider two tanks which are internally connected. So current you have this much number of, and you have here like this. But now what happens, sir? More electrons will move from here to here or not? Now what happens? So when electrons are moving now, their energy, their levels will become same. So what's happening here? From higher concentration region to lower concentration region, electrons are moving or holes are moving, whatever. So that is called the current due to non-uniform concentration gradient. Here you have high concentration, you have low concentration. So now what is happening, sir? So electrons are moving from this region to this region. Electrons are moving from this region to this region. Clear? So this is called. Now what is drift current? What is drift current? The transport of charge carriers in a crystal under the influence of electric field is called drift current. So in the previous slide also we have discussed the same. This is what? The transport of charge carriers in a crystal under the influence of electric field is called drift current. If the charge carriers are moving due to the existence of external, this is called external electric field. External electric field, it is called drift current. If the current is due to the external electric field, it is called drift current. Diffusion current, the transport of charges in a crystal due to non-uniform concentration. Just what we discussed. Here. This is non-uniform, right? Here, let's say you have 100 electrons, you have only 2 electrons here. Is there uniformity? No uniformity. Here you have highest number of electrons, here you have lowest number of electrons. So obviously these electrons is moving from one region to, that is higher level to lower level. Higher level to lower level. So when the concentration of electrons are moving from higher level to lower level, what's happening, sir? The current exists. Yes or no? Obviously, when electrons are moving, we call it as current. Flow of electrons is called current. Yes or no? Flow of electrons is current or not? Yes or no? Correct, right? So obviously, either electrons may move or charge carriers may move because of the external voltage, external electric field, or non-uniform concentration gradient. Non-uniform concentration gradient. If the current is due to the applied electric field, it is called drift current. It is called drift current. If the current is due to non-uniform distribution, non-uniform concentration, is called diffusion current. So two currents are existing. One is called diffusion current. Second one is called drift current. Drift is because of the external voltage, whereas diffusion is because of the what? Non-uniform concentration gradient. Okay, next. Mobility of charge carriers. So how? This is very important, sir. Mobility of charge carriers is very important. Now consider all should come equally, right? All circles should come equally. Sir. So that you will not have some confusion. Sometimes it is not possible to draw for me to all equal. See, all sizes are not equal. This is too big, sir. Let me do smaller one. So that you will know something. Why I am trying to draw this, sir? To explain the concept of mobility. Assume that each of the silicon or germanium atom is having extra electron or a metal. Assume that this is a metal. Sir, no sir, assume this as a metal. Each metal is having electron. So these are ions. These are ions, and these are free electrons. Do you think electron, when the electron is free, do you think it will sit silently? It will sit silently? No, sir. No. It will start moving from one place to other place in a crystal. Yes or no? When the electron, when one electron is moving in this direction, one more electron may move in this direction. When two electrons are hit here, so one may move in this direction, the other may move in this direction, or it may move, whenever, depending on your hit. So electron 1, this is electron 2. So electron 2 may come back here, or electron 2 may go here, or electron 1 may come here. So the distance traveled by the electron before hitting another electron is called mean free path. Very important to be remembered. The average distance between the collisions, or the electron, the distance traveled by the electron before colliding with any other electron is called mean free path, which is average value. Generally, we'll take average. Mean free path. My handwriting is very ugly now, but still, please bear with me. Please bear with me. This is a mean free path, or average of. What is free mean path? The distance traveled by the electron before hitting another electron is called what, sir? Mean free path. Understanding or not? Understanding or not? Now, all these electrons, I'll try to draw only electrons. All these electrons in a given metal, assume that this is a metal, all these electrons can move freely in any direction. It may move like this, 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 it may move like this. In whichever direction it wants, it can move, sir. Because there is no, but it can hit and it can travel here. So, but the average lifetime or average time, the average charge, average current is 0, because it is not moving, it is not helping for the electron to move from here to here, here to here. So average current is 0 without any external voltage. Without any external voltage or electric field. Let's assume for the same metal, uh, for my convenience, I'm trying to draw this. For my convenience, I'm trying to draw this. Let's say you're applying some voltage. Now, as you apply some voltage, all electrons will try to flow in the same direction. All electrons will try to flow in same direction. Or let me do something. Assume this is some electric field you are trying to apply. Electric field E. So now, whenever electron is moving, it gains some velocity. So velocity v. It is the velocity is due to because of what's v. So this v is directly proportional to the applied electric field. Yes or no? The velocity of the velocity, and this velocity I can call it as drift velocity. Drift velocity. Drift velocity. So this drift velocity is directly proportional to the applied electric field. Drift velocity is directly proportional to the applied electric field. Yes or no? Drift velocity is directly proportional to the applied electric field. When this drift velocity is applied is directly proportional, you have some constant of proportionality mu. This constant of proportionality, I am going to call it as mobility. Constant of proportionality is called mobility. What are the units of mobility? Mobility units. Sorry. Units of mobility is meter square. What is meter? Mobility is movement per volt second. Per volt second. So for every 1 volt applied and for every 1 second, for every 1 volt applied and for every 1 second, how much distance is traveling? Mobility. The distance, the meter square distance, the square meter distance traveled by an electron, the square meter distance traveled by an electron for every 1 volt and second, for every 1 volt of voltage, electric field, 1 volt electric field, and 1 second is nothing but mobility. Is nothing but mobility. This is very important, sir. And the units of mobility are meter square per volt second. Meter square per volt second. That is constant of proportionality. Constant of proportionality. So in some cases, how mobility varies. As time come, I am teaching. Actually, this is not required for you. Just for here, I am just trying to tell you how the mobility changes with the velocity. This is the velocity. This is a electric field. This is, let's say, this is electric field. So initially, the electric field is low. For some small electric field, it is low, but higher electric fields, the velocity becomes constant. The velocity becomes constant. So initially, it is low value, and after some time, it becomes constant. So for small values, velocity, for small values, but what happens to the mobility? What happens to mobility? This in detail we will discuss in another class, because we are running short of time. So initially it is constant, mobility is constant. So sometimes it may fall like this, and it may fall like this also. This is mu. This is due to electric field E. Electric field E. For small values, the mobility is constant. For 1000 volts, for 10,000 electric fields, so it is changing. For large values, it is almost constant, 0. It's a very important point to be remembered, and we will try to stop it here. And if you have some questions, you can ask me, or otherwise we'll move forward. And tomorrow's class we will discuss about current density J. Tomorrow's class we will discuss current density J. This is a very important concept. And we will also discuss about something called conductivity. We will discuss about conductivity. we'll discuss about conductivity, and we will do some problem. This is one important problem. This is one important problem. I want every one of you to understand this problem very clearly. Very clearly. That is the reason why I'm trying to stress you more on this. And in the next another problem, another interesting problem also we will discuss. Another important and interesting also we will discuss. And then, this is today's quote of the day. Quote of the day. Now, study while others are sleeping. This is super quote. This is super quote, sir. Study while others are sleeping. Work while others are loafing. Prepare while others are playing. Prepare while others are playing. Dream while others are wishing. Such a beautiful quote by William Arthur Ward. Understand this very seriously, sir. This is very important. Study while others are sleeping. Many people, Vidyarthinam na nidra na sukam na lajja. Swami Vivekananda says, Vidyarthinam na nidra na sukam na lajja. So don't concentrate more on your sleep. Have sleepless nights. Work hard. Work hard. Work hard. When people are loafing, some people will be chit-chatting, going here and there, wasting of their time. Wasting of their time. So don't do that. You don't do that. You focus on your work. For a engineering graduate student, for a GATE examination aspirant, this is very important, sir. And prepare while others are playing. Unnecessarily, some people might be playing earlier people used to play from PUBG or something. Let them play the PUBG. But otherwise, if today they are playing with PUBG or something, but they don't know that they are playing with their life. For a GATE aspirant, always be on your toes. Always be on your toes and prepare well. And dream while others are wishing. Other people will always try to wish something. They want to become something. But you dream and try to work, prepare, dream, try to prepare, then work hard, and then study well and reach your goal. Hit your goal very hardly. Hit your goal very hardly, sir. Hit your goal very hardly. Clear? This is very much important. Okay. All the best for all of you. I think you'll study very well. Next. So coming to this slide, this is a very important slide. We have India's number one study channels. We have many channels. As I told you, you have a Creatrix GATE channel for EEE, ECE instrumentation, Unacademy GATE for mechanical and other. This is PI and XE, and Unacademy GATE for civil engineering. You have separately. Unacademy GATE Telugu. You have a separate channel for Telugu students. Unacademy SSC and JE. And you have Unacademy for computer science students, Unacademy GATE questions, only previous GATE questions, you have separate channel. Electrical junction, Unacademy Engineering Foundation, and Unacademy Pathshala. So all these channels are very much interesting. I request all of you to subscribe for all of them. Okay. Subscribe for all of them. And this is a time and again I am repeating. This is a Telegram channel where you can get all the PDFs of classes. All the PDFs of the classes. So HTTPS TME Creatrix GATE EE. This is very important. This is very where you can get today's class notes. And finally, use this code, referral code SVS10 to get 10% of discount. On whatever the fee of the day. Clear? So I wish you all the best. We'll meet you again tomorrow at 5:30. Bye.